Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basavakalyan. Dear students, already in the previous class we have discussed about planar graphs, maximal planar graphs, outer planar graphs, maximal outer planar graphs and non-planar graphs. Even we have considered examples based on those concepts. Along with that, we have discussed some results based on planar graphs. So in detail, already we have got the clear picture about the concepts. What is planar graph? Okay, and planarity in general. So today we are going to discuss some results on planar graphs. Of course, we have discussed many results in the previous class. Along with those, we are discussing some more results. Okay, even in the previous class we have discussed the relation between the number of vertices, edges and regions in terms of P, Q, R. Okay, and also we have considered one important theorem that the Kuratowski's graphs, that is K5 and K33, are non-planar. We have proved those two results. So we have proved the graphs K5 and K33 are non-planar. So today we are going to discuss some more results on planar graphs. So one result, every planar graph contains a vertex of degree at most 5. So what is the statement? Every planar graph contains a vertex of degree at most 5. What is the meaning of this statement? If you consider any planar graph, okay, so that planar graph contains at least, what you can say, a vertex of degree at most 5. There is at least one vertex. There is at least one vertex whose degree is at most 5. What it implies? Definitely there will be one vertex of degree, either 1 or 2 or 3 or 4 or 5. Definitely. Maybe other vertices of degree larger than 5, but there will be definitely one vertex of degree at most 5. So this is the statement of the result. So I think if I consider any one example, so you will come to know it's better to consider K6. Okay, it's better to consider K6, but K6 it is non-planar graph. Okay, but what I am suggesting is that in K6 degree of every vertex is 5. Okay, degree of every vertex is 5. So like that there is at least one vertex of degree at most 5 in that way. Okay, so but you should not consider the graph K6 because K6 is non-planar. You have to consider a graph which is planar. Maybe the vertices are of higher degree, but there is at least one vertex of degree at most 5. Definitely there exists one vertex whose degree is at most 5. Okay, so other vertices may be of larger degrees. So this is the meaning of the statement. Now to prove this result, what we will do? So we will consider a graph, planar graph, which contains P vertices and Q edges. Okay, so P vertices, it implies there are P vertices. Okay, so let the vertex set of that graph contains the vertices V1, V2 and so on and so forth, Vp. Okay, now we consider two cases here. Two cases. Suppose P is less than or equal to 5. It implies the graph contains maximum 5 vertices. When the graph contains maximum 5 vertices, the maximum, or you can say the complete graph with 5 vertices is K5. Okay, that is the largest graph with 5 vertices. Of course, K5 is non-planar, but even if you consider K5, in K5 degree of every vertex is 4. It implies you will get larger degree 4 only. So there are all vertices are of degree 4 only. Though it is non-planar, but we are not considering that one. If P is less than or equal to 5, the largest graph which is non-planar is K5 minus E. Already in the previous class we have discussed. If we consider a complete graph with 5 vertices and if you delete one edge from that graph, so K5 minus E is a planar graph, and if you observe the degree of every vertex, at most 5, because the complete graph itself contains 4, every degree of every vertex is 4, it implies the result obviously holds. It implies definitely there will be one vertex of degree at most 5, because every vertex is of degree 4 only in that. So it implies, it is very obvious if you consider a graph with P less than or equal to 5 vertices. Now we are going to consider a graph in which the number of vertices are greater than or equal to 6. Okay. Now already in the statement what we have considered? We have considered G is a planar graph. When G is planar graph, in the previous class we have proved one result. What is that result? The number of edges in that graph is always less than or equal to 3p minus 6. So this already we have proved in the previous class. The number of edges in a planar graph is always less than or equal to 3p minus 6. Okay. So now if I multiply by 2, what happens? Therefore 2q will be less than or equal to 6p minus 12. Okay. So this is the result based on the previous class what we have discussed. But we know one result, one fundamental result in graph theory, that is the sum of the degrees of all the vertices is equal to twice the number of edges. This is the first fundamental result in graph theory, which already we have discussed in 5th semester in the first class itself. Okay, the sum of the degrees of all the vertices is equal to 2 times the number of edges. Okay, it implies 2q is equal to, if you compare the previous equation, so what we will get? The sum of the degrees of all the vertices is equal to 2q, but 2q is less than or equal to 6p minus 12 from the equation. Okay, it implies, what it implies? If all p vertices of G have degrees 6 or more, then what happens? If degree of every vertex is 6, so sum of the degrees of all the vertices, 6 plus 6 plus 6. So if you add 6 is p times, what it will happen? It will be 6p, but at least 6. So if all p vertices of G have degree 6 or more, then obviously 2q is greater than or equal to 6p, isn't it? So 2q is greater than or equal to 6p. This is impossible, because in the previous step we are saying 2q is always less than or equal to 6p minus 12, but we are getting 2q is greater than or equal to 6p. So this is impossible. So this proves that there exists at least one vertex whose degree is at most 5. So there will be definitely, of course, degree of all vertices may be 6 or more than 6, but there is at least one vertex whose degree is at most 5, that is maximum 5. So this is a simple proof. So here, to prove this result, what we have considered, 2 important things we have considered, or 2 important results we have considered. One is, when G is a planar graph, then Q is less than or equal to 3p minus 6. This is one result which we have proved in the previous class. And another result we have considered is, sum of the degrees of all the vertices is equal to 2q, or twice the number of edges. With the help of these 2 results, we have proved a simple result here. Okay, so now we will see some other results. So now we are considering one important result. If G is a PQ planar graph, means a planar graph containing p number of vertices and q number of edges, in which every region is an n cycle. Every region means every face. Every face is n cycle. N cycle means it is a cycle of length n. It implies every face may be 3, 3, 3, 3, or every face is a cycle of length 4, 4, 4, like that. Here you can see this example. So this is a graph, planar graph, in which every face is C4, cycle of length 4, C4. See, this is one region which is of length 4. This is another region which is of length 4. Like that, this is another region which is of length 4. And the exterior region if you count 1, 2, 3 and 4. So every region, it may be interior region or it may be exterior region. Every region or every phase is 4 cycle, means it's a cycle of length 4. Every phase is 4 cycle. So like that, if you consider this example in particular, here every region of G is 4 cycle. So how many vertices are there in this graph? 6 vertices, 8 edges and 4 faces, including interior as well as exterior. 3 interior faces and 1 exterior face, totally 4 faces. So it, and n equal to 4 because it is a 4 cycle. Every face is a 4 cycle. So n is 4. So now if you substitute these, what happens? What is the statement of the theorem? If G is a planar PQ graph, a planar graph with P vertices, Q edges, in which every region is n cycle, then the first result says Q equal to the number of edges in this graph is n by 2 into r, or you can say nr by 2. The second result, of course, in terms of Q only, the number of edges you may say in another way, n times P minus 2 divided by n minus 2. So these two results definitely holds if you substitute these particular values. Here in the first equation, if you substitute n as 4 and r as 4, so what happens? It will be definitely 8. So it implies both the results satisfy with this particular graph. Okay, so we have verified the result. It is very easy to verify because you know the value of r, we know the value of n. If you substitute, you will get Q equal to 8. Okay, so this is very easy to verify. Let us prove this result. Now the given graph is a planar graph. Now we will consider the plane graph of planar graph. You know already, planar graph means it can be possible to draw on the plane without the intersection of edges. Once if it is drawn on the plane without the intersection of edges, then that graph is called a plane graph. Okay, so in plane graph you won't get any crossings. Of course, crossing may be there in the planar graph. Of course, it is possible to draw on the plane without the intersection of edges. Then that graph is called a planar graph. Once if it is embedded in the plane, then that graph is called a plane graph. Okay, so let G1 be a plane graph. Like this example, G1 is a plane graph here. Of course, it is a planar graph, but embedded in the plane of the planar graph of G, in which every region is an n cycle. Like this in this graph, every phase or every region is 4 cycle. Okay, so thus each edge of G1, see if you observe any edge, every edge is on the boundary of definitely exactly 2 faces. Of course, it's very obvious. So thus each edge of G1 lies on the boundary of exactly 2 faces. If you observe any edge, it is lying on exactly 2 faces. So these are the 2 faces for this edge. If you consider this edge, it is on this face as well as the exterior face. So like that, if you consider this face, it is exactly on this face as well as the exterior face. So every edge is, or every edge lies on the boundary of the exactly 2 faces. It implies 2Q is equal to obviously NR, because there are R faces and each face is a cycle of length 4 type. So obviously 2Q is equal to NR. It implies Q is equal to N by 2 into R, or you can say NR by 2. So this is how the first result is proved very easily. Now if we see the second result, already in the statement it is given that G is a planar graph. So once if it is planar, already we have proved one result, that is Euler's formula. If G is a planar PQ graph with R faces, then obviously P minus Q plus R equal to 2 holds. It implies, if you reshuffle the equation in terms of R, so R is equal to Q minus P plus 2. See, this is the second equation. Already first equation, you know already the first equation. Which is the first equation? This is P minus Q plus R equal to 2 is the first equation. And R equal to Q minus P plus 2 equal Q minus P plus 2. This is the second equation. I forgot to mention the first equation, which is the Euler's formula. Okay. Anyway, doesn't matter. From 1 and 2, from one end to 2q equal to, I think already in the previous slide I have given equation 1. Okay. Yes. So 2q is equal to n times what is that? Yes, already equation 1 is there in the previous slide. If you see the previous slide, already you have got n is equal to 2q equal to nr. Okay. So therefore, I have substituted the value of r there as q minus p plus 2, and if you simplify this, you will get q equal to n times p minus 2 divided by n minus 2, because combine the q terms and separate the p terms on the other side. So you will get q equal to n times p minus 2 divided by n minus 2. So this is the simple result. So how we have proved this result? Just we have considered every phase is n cycle. So maybe 4 cycle, maybe 5 cycle. So n is 4. So how many phases are there, that you have to count. So therefore the number of edges, because one edge is on boundary of exactly 2 phases, it implies 2q is equal to nr. So 2q equal to nr. Here what we did to get the second result, instead of r, we have used the value q minus p plus 2 by Euler's formula. So this is how we have got the second result very easily. So now we will see the next result. Every maximal outer planar graph, which graph is maximal outer planar? If I consider K4 is a planar graph, and it is outer planar graph K4, and it is maximal outer planar graph because you cannot add one more edge, isn't it? Similarly, K23 is also a maximal outer planar graph, because if we add one more edge, I think K23 may not be outer planar. Okay. Anyway, that is not the outer planar graph. What I am going to say, every maximal outer planar graph, if you consider any outer planar graph, for example, C3, a cycle with 3 vertices is an outer planar graph, and it is maximal outer planar graph. Okay. How many phases are there in that? There are 2 phases. So cycle with 3 vertices, C3, it contains 3 vertices, 3 edges and 2 faces. One is interior face and another one is exterior face. Okay, C3, which is maximal outer planar graph. If you consider that particular graph, so what is the statement here? Every maximal outer planar graph with a p greater than or equal to 3 vertices has 2q minus 3 edges. It implies the number of edges will be 2p minus 3. In particular, if you consider C3 or K3, what I said, it contains 3 vertices. So 2 into 3, 6. 6 minus 3 is 3. So it contains 3 edges. Obviously, C3 contains 3 edges. You can say C3 or you can say K3, which is a maximal outer planar graph, and it contains 3 edges. So it holds. It implies we have verified the result. Now we are going to prove this result. So how to prove this result? Again, by the one of the results which we have proved in the previous class. What we have proved? We have proved every maximal outer planar graph. Of course, instead of saying outer planar, I am saying outer plane graph, because it is drawn on the plane or it is embedded on the plane. Okay. So every maximal outer plane graph with p greater than or equal to 3 vertices has how many interior faces? In the previous class already we have proved it has got p minus 2 interior faces. So the maximal outer planar graph has got p minus 2 interior faces. This is the result which already we have proved in the previous class. So based on this result, now what we can say? R is equal to, here p minus 2 interior faces. So interior faces are p minus 2. So totally faces are interior faces plus 1 exterior face. So that together considered as number of faces. Okay. So therefore the number of faces R is equal to the interior faces, that is p minus 2 plus 1 exterior face. It implies the total faces of a maximal outer planar graph R is equal to p minus 1. See, this is the first equation. Okay. Now already as G is planar, because every maximal outer planar is graph is also a planar graph. Maximal outer planar is planar graph. Obviously, it implies by one of the results or you can say by Euler's formula, if G is a planar graph, definitely P minus Q plus R is equal to 2. Again, if I write in terms of Q is equal to P plus R minus 2. See, this is the second equation. Again, from 192, you are substituting the value of R as P minus 1, equation 2. So it implies from 1 into what we have got, Q is equal to P plus R value is P minus 1. So if you substitute and simplify, what we are getting? Q equal to, it is very easy to simplify, 2P minus 3. This is how we got proof of this result. Very interesting result. Okay, so what is the result? Every maximal outer planar graph with P greater than or equal to 3 vertices has how many edges? 2P minus 3 edges. Okay, so these are the simple results. Of course, this is also one of the result based on the number of vertices, edges and regions. Okay, so now, so in this session, what we have discussed? We have discussed every planar graph contains a vertex of degree at most 5. This is one result we have proved. And the next result, which result we have proved? If G is a planar PQ graph in which every region is an n cycle, then the number of edges is equal to nr by 2, or you can say the number of edges is equal to n times P minus 2 divided by n minus 2. And one more result we have proved, every maximal outer planar graph with P greater than or equal to 3 vertices has 2P minus 3 edges. So this is how we have proved the results based on the previous results and concepts. So with this we conclude the today's session. So these are the reference books. Already in the previous class also I have told you, if you want you can refer any one of the books, or both books you can refer, or there are some other books on graph theory, so you can refer those. Okay, so with this we conclude today's lecture. Thank you.